Hey, good people, welcome to the first video of 10.5 Harmonic Series and P Series. So, in this set of notes, we'll be talking about a specific type of series, just like we had a specific type when we talked about a geometric series. We're going to look at a specific type of series called the harmonic series, which we mentioned before, and now a new type of series called the P series. So, let's start with that. So, we know we have a P series if P is a positive constant, and the sigma setup, the series, looks like 1 over n to the p. Now, what does that mean? That means that when I substitute values of n, my terms are going to look like this. So, if I know I have this type of series, which looks kind of like a geometric, we're going to see the difference here in a little bit. But if I have this type of series, which is called a p series, I know the series will converge if p is greater than 1. Now, this is a little bit different than geometric series. Geometric series, we needed the ratio to be less than 1. But here, p series convergence will rely on the fact that the p value is bigger than 1. And it's going to diverge if p is between 0 and 1, including 1. So, why does this work? What does it mean? And what's the difference between a p series and a geometric series? Remember, in the previous sections, we talked about a geometric, and a geometric could look like this. Let's make it a little bit nicer here. It could look like, I don't know, something like this, right? This is a geometric because I have a ratio that is taken to a power. And so in a geometric series, the n value is in the exponent. With the p series, I could also, before I go on to p series, we saw examples where a geometric series looked a little bit different. It kind of looked like this. This is a geometric series. I know that because I could rewrite the 1 over 3 to the n. I could rewrite it as 1/3 to the n, right? So it's the same thing, and therefore I have a common ratio. But again, what's in common between both of these setups is that n is the counter of the sigma, the n index. This is in the exponent position. That's different than a p series, and in a p series, it's not the exponent that's the n, it's the base that's the n, right? So it could be something like n to the third. This is a p series because the base is the one that's changing. The p is the constant exponent that doesn't change. And because of what we wrote down, p is greater than 1, this is a convergent series. Now, why does that work? It works because of the integral test. The integral test says, hey, I can do an integral from 1 to infinity of 1 over x to the third. Can I find the antiderivative of this? Well, sure. If I rewrite this as x to the negative 3, and then I can take the limit as b approaches infinity. Here, why don't I leave it this as 1 over x to the third, and then in this step, I'll change the limits of integration here, and I'll change my integrand, and I'll add 1 to the exponent, divide by the new exponent. We're going to evaluate that from 1 to b, and we're going to take the limit of that expression. So really, we're taking the limit of that expression, and this is 1 over negative 2x squared. So I'm going to substitute the b first, minus 1 over negative 2, 1 squared. And I notice that, as b goes to infinity, this first part is going to go to 0, so that's gone. So then my answer really is just negative 1 over, I guess it's positive, 1 over 2. So this integral converges. So therefore, this p series, this infinite series, converges as well, right? So instead of doing the integral test over and over again, we just recognize that if the exponent here, the p value, is bigger than 1, it is going to converge. Well, what if it's equal to 1? Well, if it's equal to 1, then we get the harmonic, right? If I go from 1 infinity, 1 over n to the 1, Well, we usually don't put that 1. We just leave it like this. And this is the same thing as 1 plus 1/2 plus 1/3 plus 1/4 plus so on and so forth. And this always diverges. We had already shown that by the integral test. Always diverges. So this is a harmonic series is a special type of p-series, which we know always diverges. And if the p-value is equal to 1 or the p-value is less than 1, it's going to diverge. That's all a p-series is. So using the integral test, we're able to prove that a p-series converges or diverges. A special case of a p-series is when p equals 1. That would be the harmonic series, and that would be that. So when I look at number 1, does a series converge? Well, my p-value, p is equal to 3, and that's greater than 1, so yes, converges. Or when I look at this, well, I don't see an exponent. However, you and I both know that I could rewrite this as 1 over n to the 1/2. So therefore, my p value is 1/2. That's less than 1, or I guess in between 0 and 1, and therefore it's going to diverge. That's the p-series test, I guess, if you will. So in the next video, we'll look at how to use this idea to determine k values where the series is going to converge, and then we'll wrap it up to where we are up to this point.